we're going to introduce the Wilcoxon Signed-Rank Test. This test is a non-parametric alternative to the paired t-test. So here we want to compare two groups on some numeric value that are paired or dependent in some way. So we're going to continue on this example where we're looking at systolic blood pressure as measured before and after receiving some treatment. We use this approach for a few reasons. If we have a small sample size, and we can't work with a parametric approach, that's one reason. Or if we'd like to test the hypothesis about the median change rather than the mean. So just a reminder of parametric versus non-parametric approaches. Non-parametric approaches tend to have lower power, meaning if the null hypothesis is false or the alternative hypothesis is true, the non-parametric approach is less likely to conclude that than the parametric approach. But one of the pros of these is they make fewer assumptions. They don't require large sample sizes. They don't assume normality. So that's kind of the nice side of them. And also a reminder, aside from non-parametric approaches, we could work with bootstrapping or resampling type approaches if we don't have large sample sizes or if we don't want to make as many assumptions, normality being one of them. So we're going to work our way up to the Wilcoxon Signed-Rank Test. And while we're going to do some of the calculations, we want to focus on the concept underlying this test as well as just non-parametric approaches in general. So recall the paired t-test we were testing is the mean difference 0. And here we're going to get at the median difference. And before getting into the Wilcoxon Signed-Rank Test, we're going to start with the simplest form of a non-parametric approach, the sign test. And this test is probably a little bit too simple to be useful, but it's a good building block for what is a non-parametric approach. So this tests the same null and alternative. It tests a null hypothesis that the median difference is 0 versus an alternative that the median difference is not 0, or in this case, we'll test less than 0. Okay, we'll do a one-sided hypothesis test. So all this test does is, we can see over here, when we look at the changes in the after minus the before measurement, some people had increases, some people had decreases. Okay, so it just looks at the sign. Was there an increase or was there a decrease? Okay. So if we look at the signs, okay, or the changes, we'll see that, let's change our color here. We'll see that what we've observed is that for the decreases, there were 8 individuals who experienced a decrease in their systolic blood pressure after treatment. And for the increases, if we count them up, there were 3. Now what the sign test does, it says if our null hypothesis is true, right? If the median change or the median difference should be 0, then what we'd expect to see, again, if our null hypothesis is true, is that half of the people should show a decrease, half should show an increase, right? If there's, in theory, no difference between before and after, we'd expect to see some people go up, some go down, and it to be about a 50-50 split. So we'd expect, out of our 11, 5.5 to show a decrease, and 5.5 to show an increase after treatment. So now we can work out the p-value for this. And p-values, while the calculation of them changes slightly, the underlying concept is always the same. What's the probability of observing what we did in our sample, or something even more extreme or further from the null, if the null is true? So here, we want to work out what's the probability of seeing 8 or more, let's just say decreases, right? 8 or more people showing a decrease after treatment. If the null is true, okay, in that case, if we should observe 5.5. So what's the probability of seeing 8 or more people showing a decrease after treatment if in theory we should have seen only 5.5? You may build this connection or notice that this follows a binomial distribution. Binomial models things that either occur or don't occur. right? There's a decrease or there's not a decrease. The probability of a decrease is constant, in this case 50%, and each trial is independent. Each person showing an increase or decrease is independent of the others. So here we can work out for a binomial, what's the probability of seeing x greater or equal to 8, given that, again, x is a binomial with 11 trials, 50% chance probability of success. If you work this out, you're going to find it comes out to be 0.11 or 11%. So there's about an 11% chance of seeing 8 or more people showing a decrease, if in theory it should have been a 50-50 split and we should have seen about 5.5. Okay, reminder, this is the one-sided test. To do the two-sided test, we double that p-value. But one thing to note about the sign test is it's a little bit simple. Okay, it only looks at was there an increase or a decrease, but it ignores the magnitude of the change. So in other words, it treats a decrease of 3 in blood pressure the same as a decrease of 30. Okay, it doesn't differentiate between those two. We're going to highlight the problem of the simple sign test here. So I'm going to create an exaggerated example. So I'm just going to label this example number 2. And we're going to consider a sample size of 7. Again, this is going to be exaggerated to draw out a point. Suppose we saw someone had a decrease of 20, an increase of 1, a decrease of 18, an increase of 2, a decrease of 10, an increase of 1.5, and a decrease of 14. One thing you can notice here is that we observed 4 people showing a decrease, 3 people showing an increase. And if our null hypothesis is true, what would we expect? We'd expect 3.5 people to show a decrease, 3.5 to show an increase. Okay, so what we observed is perfectly in line with what we'd expect under our null. But what do we notice here in this exaggerated example? There were 4 people who seemed to, the drug seemed to be really effective for them. They had a pretty large decrease. And there were 3 people whose increase was negligible. Okay, it looked like not much change. Okay. So this is an exaggerated example meant to draw out a point. Okay, that this simple sign test ignores the magnitude of the change. So we saw that the sign test was a little bit too simple in that it ignored the actual magnitude or size of the change. So we're going to look at the Wilcoxon Signed-Rank Test. Okay, so we're going to add in the ranks to the signs. So essentially what we're going to do is we're going to take a look at the changes that we've seen. Okay, in either one of these examples, example 2 or example 1 here. Okay. And we're going to rank the changes in absolute size or absolute magnitude. So what's the smallest change? What's the second smallest change? What's the third smallest change? And so on. And we can rank them from smallest to largest or largest to smallest. It doesn't really matter. Convention is usually smallest to largest, but like I said, it doesn't make a difference. So what we're going to do is rank the size of the changes, and then we're going to sum up the ranks for all the decreases, sum up the ranks for all the increases, and compare those two. If the null is true, we've already noted that we're going to expect about half the people to show an increase, half to show a decrease, and in terms of the ranks, we're going to expect the small ranks, right, the small changes, to be equally distributed amongst increases and decreases. Same with the large ranks, or the large changes. If the null is true, we'd expect to see large decreases and large increases. So let's look at doing this. First, we'll do it on our simple example here, and then after that, we'll move to doing it on the slightly larger example. So here, I'm going to add in the ranks. So first, let's find the smallest change. That's this one here. Then the second smallest change, again in absolute value, is here. The third smallest change. The fourth smallest. The fifth smallest. The sixth. And the seventh. Okay, and the convention is if 2 observations are tied, suppose that there were, say, 2 decreases of 14, showing the 5th and the 6th rank. We average those two. Okay, but again, we don't want to focus too much on the mechanics. We want to focus on the concepts. We can let software do the mechanics for us. So now, let's get to first this one here, example, what we're calling example number 2. Let's talk about what we'd expect if our null hypothesis is true. We'd expect to see about half the people showing a decrease, half showing an increase. If we sum up all these ranks, 1, 2, 3, 4, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, we're going to find the sum of those comes to 28. And we said we'd expect them to be evenly split amongst the increases and decreases. Okay, in other words, we'd expect the sum of the decreases to be about 14, and the sum of the ranks for the increases to be roughly 14. Now, let's take a look at what we observed in our sample. We saw for the decreases, they've got a rank of 7, 6, 4, and 5. So if we sum up all of the ranks for the decreases, those are going to come out to be 22. And if we sum up all of the ranks for the increases, those are going to come out to be 6. So again, we can calculate a p-value here, and that p-value tells us what's the probability of seeing, say, the sum of the negative ranks being 22 or more if, in theory, the null was true, and it should come out to be about 14. So again, let's write that here. The p-value is going to tell us what's the probability that the sum of the negatives is greater or equal to 22 if, in reality, the null is true, and it should come out to be about 14. And again, there's tables to find those exact values. Let's not worry about the mechanics of it. Okay, let's focus on the concept of what is this test trying to do. Okay, so we can see it's comparing the signs, the decreases and the increases, but also incorporating the ranks. Okay, were the decreases large or small? Now, let's get to looking at the larger example we have here. We can see that we have all of these differences, and over here, if we include the rank, again, the rank of the absolute changes, if we take a look here, we're going to see that there's an increase of 3 and another increase of 3. And those are tied for the first rank, right, the first lowest rank, and the second lowest rank. So what we do is we assign those the average of their shared ranks. So they're both going to be given the 1.5 rank. So first we've got this one here, and it's in the 1.5 rank, and it was showing an increase. So I'll just add that there. And then the other one we have here is sharing the 1.5 rank, and it's an increase. So I'll put a plus there. Then the next lowest ranks, there's a decrease of 4 and another decrease of 4. So those are sharing the third rank and the fourth rank. So we're going to assign them the average of the ranks, the 3.5 rank. That's right here. And it's a decrease. And then this one here, sharing the third and fourth rank. After that, the next smallest change is the decrease of 6. Okay, so this is sitting in the 5th rank, or the 5th smallest change. Okay, and we can see that one right here. So again, that's in the 5th rank, and that was a decrease. Then we can say that there was a decrease of 8 and an increase of 8. And those are sharing the 6th rank and the 7th rank. So we're going to assign the average the 6.5 rank. So we can see this one here is ranked 6.5, and it was a decrease. This one here is the 6.5 rank, and it was an increase. Then we can see the next smallest one is the decrease of 11, and that's in the 8th rank. Again, it was a decrease. Then the decrease of 12 here, and that is in the 9th rank, and that was showing a decrease. Then the decrease of 15, and that's sitting in the 10th rank, There's a decrease. And then the decrease of 22, which is the 11th, right, or the largest rank. And again, it was a decrease. So let's take a look at doing the same here. So this is what I'm labeling example number 1. Now, first let's think about what we expect if the null is true. So if we sum up the ranks 1 plus 2 plus 3 all the way up to 11, that's going to come out to 66. Right? And if our null is true, we'd expect about half the people to show a decrease, half to show an increase, and we'd expect the large and small ranks roughly equally balanced. So we'd expect the sum of the decreases to be about 33, and we'd expect the sum of the increases to be about 33. Now, what do we observe in our sample? When we actually did this for our observed data, we saw that the sum of the decreases, that's going to come out to be 56.5. And the sum of the increases came out to be 9.5. And so again, we can calculate a p-value, which tells us what's the probability of observing what we did in our sample, or something even further from the null, or more extreme, if the null is true, and this is what we'd expect to see. So we can calculate p-value. Again, this tells us what's the probability of observing the sum of the negatives being greater or equal to 56.5 if, in reality, the null is true, and we'd expect that it should come out to be roughly 33. If you work this out, okay, so if you take this data, put it in software, and ask it to do the Wilcoxon Signed-Rank Test, you're going to find that the p-value here comes out to be 0.0203, or 2.03%. Okay, and again, a reminder, this is for the one-sided test. If you did the two-sided test, it would be double. We're going to end up reaching the same conclusion. Since our p-value is small, we're going to reject our null hypothesis. We reject our null. We have evidence to believe the alternative is likely true, right? Or the median decrease is less than 0. People are experiencing some decrease after treatment. So again, just a final reminder, doing this stuff by hand is not important. Okay, it's a distraction from your learning if you try and focus on how do I calculate all these ranks, sum them up, and so on. What's important is the concept and understanding how is the non-parametric approach trying to get at the same question that the parity test or the parametric approach did. All the different non-parametric tests you can encounter, the parts change slightly. The underlying concept is generally the same. They usually work with ranking observations rather than the numeric values themselves. There's gains and losses to these. Right? By ranking the observation, the gain is it becomes less sensitive to outliers. Right? Whether the largest change was a decrease of 22 or a decrease of 42. Right? Either way, this is going to be the largest change. So it doesn't become sensitive to an outlying value or an extreme value. So in some way, that's a gain. A negative of using ranks is it throws away some information. Seeing a decrease of 22 or a decrease of, say, 26, those are slightly different pieces of information. Right? The decrease of 26 might be a bit more informative or a bit larger, and you're kind of losing some of that. So gains and losses to these non-parametric approaches versus parametric. But just a reminder, they're a slightly different way of getting at the same problem.
Hope you guys liked the video. Subscribe to our channel, like our videos, share our videos. Statistics is almost as beautiful as a unicorn. Stick around, guys, because we got lots more.